Okay, so one of the most important concepts in numerical analysis is the Taylor series expansion, because it does educate us in many equivalent concepts that go hand in hand, and one of them is the error calculation or error prediction. It does help because a function, according to the Taylor series expansion, it needs an expansion of an infinite number of terms, for which, practically speaking, we don't have enough paper to write an infinite number of terms, we don't have enough computer storage to do that, but in principle that's what we need to write, which is defined as evaluating any function at point x. It can be written as an expansion of the values of the function and its derivatives evaluated at the point x0. So let's assume that we know the value of the function here at point x0, and this would be the fx0, and we want to know what is the value of the function at x, somewhere here, knowing only the values of the function at x0. So assume that we have a function such as cosine x, and the first thing that we need to figure out is to figure out what are the nth derivatives of this function. In this case, the first derivative, the second, the third, the fourth, and so on. So the first derivative of the cosine x is minus sine x, then the next derivative is minus cosine x, then we have sine x and cosine x. Then what we need to do is that, for example, if we are given the value of the cosine at pi over 4, so let's assume that we have a function here at pi over 4. We know that the cosine, it has such a curve. We need to get what is the cosine at pi over 3, and let's see how we can solve this problem. And for this we do the following expansion. We say that the function at pi over 3 is equal to cosine at pi over 3, and this is equal to the, let's try to expand this term here. We have the, for n equal to 0 term, when n is equal to 0, let's see what this expression gives for us. This means that the zeroth derivative of cosine x, which means that is the function itself. When it takes the zeroth derivative, that means it is the function itself. So this is going to be equal to cosine evaluated at pi over 4, because x0 is pi over 4. So x0 here is pi over 4, and what we really care is the other term, which is x minus x0, which in this case is going to be pi over 4 minus, pi over 3 minus pi over 4, because we are doing the expansion over there, and this is going to be something like pi over 12. Let's go on. The zero derivative, we get this divided by 0 factorial, which 0 factorial by definition is 1, and we multiply here x minus x0, which, let's write this one, x minus x0 is equal to pi over 3 minus pi over 4 all to the power 0, which should be equal to 1. So then this is the zeroth order approximation. That's what we call this one. The zeroth order approximation, in this case, it would be equal to just cosine of pi over 4. Cosine of pi over 4 is equal to square root of 2 over 2, which makes something around like 0.7071. So, but then this is if we take only the first the zeroth order. If we expand for more terms, let's assume that here the f evaluated at pi over 3, which is equal to cosine evaluated at pi over 3, this would be equal to the n equal to 0 term, which is, as we wrote above, this should be equal to cosine pi over 4. Let's see what we had above. So this was the n equal to 0 term, which means that this is the zeroth order approximation, plus the n equal to 1 term, the second term. This would mean that we have to include the first derivative of cosine, which we see it here. The first derivative is minus sine. So here we have minus sine of pi over 4 divided by 1 factorial, and then this is pi over 12 to the power 1. This would be equal to whatever the cosine of pi over 4 was, which is 0.7071, minus square root of 2 over 2, which is sine of pi over 4, times pi over 12, which is equal to 3.14 over 12. So here we get the first order approximation of this function, and this one would be equal to a value of around 0.52199. Now, for these two cases, we do need to calculate the error propagation. So the error for the zeroth order approximation, it's going to be equal to the true error percent rate. This is going to be equal to the absolute value of the exact value 0.5 minus 0.7071 divided by the true value multiplied by 100%, and this would give something, an error rate of 41.4%. So we get quite a considerable amount of error. And here in this case, we just use the fact that the cosine of pi over 3 is equal to 1 over 2. So actually, in this case, the cosine of pi over 3 is a number which we know it with infinite precision. We say that because this one can be described as a ratio of two integer numbers or as a rational number, whereas the cosine of pi over 4 is square root of 2 over 2, which means that we are quite limited in determining with infinite precision this number. Now let's go ahead. It looks like in this case the error, it looks like we get a little closer, and the true percent error rate, it would be 0.5, the true value, minus the approximated value, which we got it using only two terms in the Taylor series expansion. We get 199 divided by the true value, which is 1 over 2 or 0.5 times 100%. And the answer that we get here, for sure it could be something better. We get something in the order of 4.4% true error rate. Now let's move ahead and let's see what we get for the function evaluated, pi over 3, which should include now, which is equal to the cosine pi over 4, which was here, which in principle is square root of 2 over 2, minus what we got here in the square root of 2 over 2 times pi over 12, which is 3.14 over 12, and then we have to include the other term, which in this case is going to be plus the second derivative of cosine, which is equal to the minus cosine, and minus cosine of pi over 4 divided by the 2 factorial, because n is equal to 2, times pi over 12 square. So in this case, we can write this one as square root of 2 over 2. We can factor this out, 1 minus 3.14 over 12 minus, so this cosine, this goes in the front, 1 over 2, then we have 3.14 square divided by 12 square, and as a result, finally, we get something in the order of 0.4979. So, and if we want to calculate the true error rate, so this was this result, we get here the ET, this is going to be something like 0.4979 minus 0.5 divided by 0.5 times 100%, we get something in the order 0.4%. So this is the error that we get in the calculation of such a term, which means that as we are trying to identify this figure, we can see, or we can observe a result which looks more or less like in this figure here. So if we try to look carefully here, what we do have is that this is the cosine function, and we are trying to determine, we are given this value for pi over 4, which is this value here, and then we're trying to determine this one, which is, as we said before, we know with infinite precision is 1 over 2. The zeroth order approximation, it's right here, which is the value of the function itself. So this is the zeroth order approximation. The first order approximation, based also on the calculations that we just show here above, is going to be a point here, which looks like it's a little more than 0.5. then the next order approximation, we notice that the value that we got, it was 0.4979, so it's a little lower than this point of interest, but so it looks like the second order approximation we get a smaller value, and in the next if we include a further order in the Taylor series expansion, most probably this error does decrease, but the message that we want to give here is that for such a function which has an infinite number of derivatives, which means that it's infinite, we can take the derivative an infinite number of times. So for such a function, that means that we need a lot of approximations, but for sure what could be assuming as a given is that more terms in the Taylor series expansion, closer we do get at the correct answer. Now, since we are considering here this Taylor series expansion, let's assume also for a moment that we have a function of the first order. If we have a function of the first order, such as f of x is equal to 3x plus 7, assume that we are given the function f of x 0. This can be evaluated at pi over 4, which in this case would be 3 times pi over 4 plus 7. This would give some specific value, but assume that we want to know what is the value of the function pi over 3. Then this value at pi over 3, the first order approximation, it would be, so the first order approximation is going to be this is the normal, this is over n factorial. Again, we have pi over 3 minus pi over 4 to the power n. So for n equal to 0, what we are going to get here is the 0th order derivative of this function of 3x plus 7 is the function itself. So the function itself evaluated at pi over 4, this is going to be 3 pi over 4 plus 7 divided by 0 factorial times pi over 12 to the power 0, which really means that this is 3 pi over 4 plus 7. Meanwhile, if we want to include one further linear approximation, is the following. So we start with including the n equal to 1 term. We have the 0th order approximation, which is 3 pi over 4. This is 7 plus 7 plus the first order derivative of this function. This is equal to 3. Okay, so that's all we get. Then the first order derivative, this is going to be 3 evaluated at pi over 4. So this derivative at pi over 4, because let's not forget our x0 is the pi over 4. This function, this is a constant, at this value is still going to be 3, okay, but this is over 1 times pi over 12. The answer is going to be something like 3 pi over 4 plus 7 plus 3 times pi over 12. Now, if we want to include one further term in the Taylor series expansion, we would have the 0th order result, which is 3 pi over 4 plus 7 plus 3 pi over 12 plus the next order is that we include the second derivative of the function f. Now, if the first derivative was this, the second derivative of 3 is equal to 0. So this means that if we add another term 0, that means that we're going to get no further improvement in approximating the value of the function at pi over 3 using the value of the function and its derivatives at pi over 4. So this means that probably we can stop here, and since we get these 0 terms, that means that if we do truncate all the other terms beyond the n equal to 2, n equal to 3, and furthermore, that means that we are not taking away anything in terms of the precision. But if you look here at the previous example, when we had this cosine, at least the result that we have shown so far in this calculation, that means that we have truncated, or we have taken out all the terms beyond the second order term, which means that here, for example, we have excluded the Taylor series expansion for n3, n4, and more. But in this case, this means that if we are dealing with polynomials that have a limited number of derivatives which are non-zero, that means that this also teaches us of how much Taylor series expansion terms we do need to take. And similarly, if we have another function which is a third order polynomial, such as f of x can be, for example, 3x cubed minus 2x plus 7. So if we want to do the Taylor series expansion of such a function, pretty sure we just need to count how many derivatives we have to work with. So the first derivative of this function is going to be something like 9x squared, the next minus 2, the next derivative is going to be like 18x, the third derivative is going to be equal to 18, the fourth derivative is going to be a 0, which means that this much term is going to be enough. But let's also say that we have to include also the 0th order derivative, which is the function f of x itself. So it looks like a third order function. If we use the Taylor series expansion, that means that we can write the expansion of any function with only 4 terms, if it is of third order or if it is a polynomial. Now from this picture we also do figure out or notice that any function which is a polynomial is a pretty nice piece of function to work with. Okay, so if we can expand other functions in terms of a series of polynomials, this is very it's easy to work with because it's easy to take the derivative out of it, it's easy to integrate them. But if you have other functions which cannot be expressed as polynomial, they are a little more tough to work with. They have more problems appear when we are working with them. And for these simple reasons, in more advanced topics of numerical analysis, we do notice that many spatial or many useful functions or polynomials have been developed, such as Legendre polynomials, and I cannot remember any other polynomials, but right now I can say that we have Legendre and many more. And that's the beauty of those, because expressing something in terms of polynomials, it provides an immediate simplifications of the tools that we have at work.